Motion in one dimension. All right, the question I have for you. Is this iPad moving?
Yes.
No, yes, which is it? What is it, people? Come on, you're the smartest people around.
Yes.
Actually, both answers are correct. So, somebody justify their yes answer.
Slide aside.
Oh, okay, no, we're not going to count wiggles and wobbles. So somebody justify their yes answer. Stephen. It's hurtling through space at an alarming rate of speed. Yes, it is hurtling through space at an alarming rate of speed, orbiting that big bright star nearest us, Sol. Okay, somebody justify their no answer. It's sitting right on top of the projector videotaping this lecture. Not moving. Okay. Motion is always relative to some frame of reference. So, if we talk about the frame of reference as being the Earth, then that iPad is not moving at all. It's sitting very still. It's not moving with respect to the Earth. If we talk about the frame of reference as being the Sun, it's hurtling through space at an alarming rate of speed. If we talk about that point of reference as being the center of the universe, then our sun is hurtling at an alarming rate of speed. So it all depends on your frame of reference, whether or not something is moving. And we're going to talk about motion always referencing some other point. When we talk about motion, we perceive motion in 3 dimensions. And those are the good old Cartesian X, Y, Z. You can do the thing we used to do in chemistry, the X, the Y, and Z. We didn't do that. That whole year. Okay, so you get your x-axis, your y-axis, and your z-axis is coming out at you. For right now, we're going to deal with motion on one of those axes at a time. In the next chapter, we'll work up to 2 axes at a time. If you're nuts enough to want to go 3 axes at a time, you're going to do that on your own time. Because we're not. Okay. When we think about motion in one dimension, we're thinking about coming forward, going back, coming forward, going back. This is a car on a track. We're not going up or down or left or right. We're just going forward and back, forward and back. The displacement is how far you are when you finish from where you start. So it's that x position final minus x position initial. That's different, you're going to see, than the distance you travel. So, it doesn't matter how far you go. Your displacement is the difference between your starting position and your final position. So, from yesterday, 3rd period, Mr. Barnhouse, what is your displacement? In 3rd period? Sitting right in that desk? Were you sitting in that desk 3rd period yesterday?
Oh, yeah, beginning of 3rd period.
Okay.
Yeah, I like that.
No. So what's your displacement from yesterday to today?
No.
0. You've gone no place. Overall, from day to day. You wake up every morning in your own bed, you stick your little feet out on your own little floor next to your bed, guess what your displacement is? Zip. You've gone nowhere. Now, you've gone lots of places. You've covered lots of ground. You may have been, to Cleveland and back. You may have been to the moon and back. Doesn't matter. If you're right back where you started, your displacement is 0. Because displacement is just looking at difference in final and initial position. It is different than the distance you cover. Okay. Now, this is an equation that you've known since physical science. You've used it since physical science. It's average velocity. If you drive to California, you decide that's it, I've had it, I'm throwing in the towel. Mr. Malcolm, you walk out from school, get in the car, your car, somebody else's car, I don't know, and you point your nose west and off you go. And 3 days later, we get a postcard from you. We can figure out the average velocity for your trip. Doesn't matter if you stopped every couple miles. Doesn't matter if you drove it straight through. We can figure out your average velocity for the entire trip because it's just your displacement divided by the time it took you to get there. Okay, so V sub A, we use a lot of those subscripts in physics. V sub A is average velocity. is equal to delta x, your change in your x position, over delta t, your time interval. We can also break that out, and this will become important as we derive some other equations, into your average velocity is equal to your final position minus your initial, divided by your final time over your initial time. So we can delta x is nothing more than x final minus x initial. Okay, on page 44 in your book are some problems. We're going to walk through one of them together. That lovely packet that I handed you, page 2A, the front page, is the same kind of problems. Your assignment will be the odds for that. So let's go to the board, and we're going to work on